Air flows over an aircraft wing, and somehow this produces lift, an upward force strong enough to hold tons of metal in the sky. The question engineers actually need answered is this: how much lift does a given wing shape produce at a given speed? Here's the pattern to recognize. This single question secretly needs almost every tool from this module. Vector calculus to describe the 3D flow, complex analysis to handle the wing's 2D cross-sectional shape, and residues to extract the one number that matters, circulation. Picture air as a vector field, an arrow of velocity at every point in the space around the wing. Divergence enters first. Air is approximately incompressible. It doesn't pile up or vanish anywhere. So, divergence of V equals curly dP by curly dx plus curly dq by curly dy plus curly dr by curly dz equals 0 everywhere in the flow. Pattern to recognize. Incompressible flow always translates directly to divergence of V equals 0 everywhere in the domain. The divergence theorem enters next. If you drew a closed box anywhere in the air around the wing, the total flux in equals the total flux out because divergence is 0 throughout the volume. Written out, double integral over the closed surface of V dot ds equals triple integral over the volume of divergence of V d volume equals 0. This is mass conservation, expressed using pure vector calculus. Away from the wing surface itself, the airflow is also irrotational, meaning curl of the velocity field is 0. Pattern to recognize. Curl equals 0 is exactly the conservative field condition from earlier in the module. It means the velocity field is secretly the gradient of some hidden scalar function, the velocity potential. Recall the key theorem, curl of gradient of phi equals 0. The velocity potential is phi, and the flow direction is simply its gradient, v equals gradient of phi. An aircraft wing's cross-section, sliced straight through, gives a 2D shape, and airflow around this shape can be modeled almost entirely using 2D complex functions. Pattern to recognize, a 2D vector field that's both divergence-free and curl-free is exactly the condition for a complex function to be holomorphic. Define the complex potential, combining the velocity potential phi with a partner function a psi called the stream function. Omega of z equals phi of x, y plus I psi of x, y. The Cauchy-Riemann equations apply directly. Curly d phi by curly dx equals curly dp psi by curly dy, and curly d phi by curly dy equals negative curly dp psi by curly dx. This is the deep overlap the module has been building toward. The vector calculus conditions, 0 divergence and 0 curl, and the complex analysis condition, holomorphic, are the same statement, just in two different languages. Since Cauchy-Riemann holds, omega of z is holomorphic. Airflow around a plane circle is easy to describe using complex functions, but airflow around an actual wing-shaped cross-section is hard. The trick is to use a conformal map to bend a simple circle into the actual wing shape. Conformal map condition recalled from earlier. F is conformal at z0 if f prime of z0 does not equal 0. The Joukowsky transformation does this bending. W equals z plus b squared divided by z, where b is a constant related to the airfoil's thickness. Pattern to recognize. Since conformal maps preserve angles, the clean flow pattern already solved around the circle carries over, distorted but still valid, onto the new wing shape. Before mapping to the airfoil, we need the flow solution around the easy shape, a plane circle of radius a. Omega of z equals v times z plus v times a squared divided by z plus open bracket, I gamma divided by, open bracket 2 pi close bracket times log of z. Here v is the free stream flow speed and gamma is circulation, built into the model using the log term. Picture walking all the way around the wing's boundary and measuring how much the air is swirling along with you as you go. This total swirl is called circulation. Pattern to recognize, circulation is nothing but a closed-loop line integral of the velocity field, exactly the left-hand side of Green's theorem in 2D, or Stokes' theorem in full 3D. Green's theorem, 2D form, the closed-loop integral over C of f dot dr equals the double integral over d of open bracket curly dq by curly dx minus curly dp by curly dy close bracket dA. Stokes' theorem, general form, the closed loop integral over C of f dot dr equals the double integral over S of curl of f dot ds. Since the flow is curl-free almost everywhere, Green's theorem tells us this circulation only depends on what's happening right at the wing's boundary, not on the details of the flow far away. Circulation, defined directly, gamma equals the closed loop integral over C of v dot dr. Here's the connection tying everything together. The complex velocity potential around the wing behaves almost like an ordinary holomorphic function, except right at the wing's location, there's a necessary singularity built in to produce circulation. Pattern to recognize: circulation, calculated as a closed-loop integral, is exactly what the residue theorem was built to compute. The loop integral collapses down to 2 pi I times the residue trapped inside. Residue theorem applied directly, the closed loop integral over C of f of z dz equals 2 pii times the sum of residues at the poles z sub j. Applied to the complex velocity, the closed loop integral over C of d omega by dz equals 2 pi times the residue at z naught of d omega by dz. Simple pole residue formula recalled from earlier. The residue at z naught of f equals the limit as z approaches z naught of open bracket z minus z naught close bracket times f of z. Differentiating omega of z, the complex velocity is d omega by dz equals v minus v a squared divided by z squared plus I gamma divided by open bracket 2 pz close bracket. This has a simple pole at z equals 0 from the log term. The a squared over z squared term is an order 2 pole, and it contributes nothing to the residue, since a residue only ever picks up the coefficient of the 1 over z part. So the residue comes entirely from the log term. The residue at 0 of I gamma divided by open bracket 2 pi z close bracket equals I gamma divided by 2 pi. Substituting into the residue theorem, the closed loop integral over C of d omega by dz equals 2 pi I times open bracket I gamma divided by 2 pi close bracket, which equals negative gamma. Notice this result is a real number, negative gamma, with no imaginary part at all. Now here's a correction to a commonly misstated step. Since this contour integral evaluates to the real number negative gamma, its imaginary part is exactly 0, not gamma. So the circulation cannot come from taking an imaginary part here. There simply isn't one to take. Checking directly using the complex velocity relation d omega by dz equals u minus iv, where u and v are the actual velocity components, multiplying out open bracket u minus iv close bracket times open bracket dx plus I dy close bracket gives open bracket u dx plus v dy close bracket plus I open bracket u dy minus v dx close bracket. The real part of this is exactly the circulation integral u dx plus v dy. The imaginary part is a separate quantity, the outward flux, which is 0 here since there's no source at the origin, only a vortex. So the correct relationship is gamma equals negative the real part of the closed loop integral over C of d omega by dz. This matches the residue calculation exactly, negative of negative gamma equals gamma, and it was independently confirmed by directly integrating u dx plus v dy numerically around the circle, which reproduces negative gamma to machine precision, with the imaginary part landing at 0. This residue isn't just abstract algebra anymore, it directly represents the physical circulation strength around the wing. Once circulation is known, extracted using the residue theorem, the Kutta-Joukowski theorem converts this single number directly into lift force. Lift per unit span equals RHO times V times gamma, where RHO is air density, V is free stream flow speed, and gamma is circulation. Pattern to recognize: every tool in this module funnels into this one final multiplication. Vector calculus set up the physical rules, complex analysis and conformal mapping reshaped a hard problem into an easy one. The residue theorem extracted the one number that mattered, and this simple physical formula turns that number into something an engineer can build a wing from. Now the worked numerical example. Suppose a circular cylinder of radius a equals 1, in a flow of speed v equals 20 meters per second, with circulation gamma equals 4 pi meters squared per second, and air density RHO equals 1.2 kilograms per cubic meter. Step 1. Circulation is already known, extracted via the residue at z equals 0 of the log term in omega of z, so gamma equals 4 pi. Step 2. Apply the Kutta-Joukowski theorem directly. Lift equals Rho times V times gamma equals open bracket 1.2 close bracket times open bracket 20 close bracket times open bracket 4 p close bracket. Step 3. Multiply the constants together. This equals 96p. Step 4. Evaluate numerically. This is approximately 301.6 newtons per meter of span. Final answer. Approximately 301.6 newtons of lift per meter of wingspan. Every theorem in this module, divergence, curl, gradient fields, Cauchy-Riemann, conformal mapping, Green's and Stokes theorem, and the residue theorem, all work together to answer one real engineering question.